Hi everyone, welcome to this video and welcome to my channel. So in this video we are going to discuss about something which is really popular in the world of computer networking, and I believe all of us have used it in one form or the other. It's called network address translation, in short NAT. So in this video we'll try to understand what is NAT, why is it required, and how it works. And not only that, the other primary focus of this video will be to understand the STUN protocol, what is the STUN protocol and how it works. STUN stands for Session Traversal Utilities for NAT, and we will try to write a STUN client from scratch in C. So yep, as always, without further delay, let's get started. Okay, so let's start with understanding what is NAT and why is it required. So when IP or the Internet Protocol and the concept of IP addresses first came into existence, what we had was the IPv4 addresses, right? So IPv4 addresses are pretty much 32-bit addresses that are assigned to machines for IP-based routing. A typical IP address would be something like 172.16.8.1, something like this, where each of this component consists of 1 byte, and so in total it's 32-bit. And on top of this, what happened, people started defining different classes of IP addresses. Like we have got class A, class B, class C, class D, class E IP addresses. So these classes pretty much determine how many octets will be reserved for the net address or the network address, and how many octets would be reserved for the host address. And this wasn't that much flexible, and then people came up with something called the classless addressing or the CIDR notation, where you are free to choose a network mask which determines the length of the network address and the host address, right? So far so good. Now the problem that IPv4 started facing was its limitation of the number of IP addresses. Like, so with 32-bit there was only so many IP addresses which you could assign to the clients, and the world soon started running out of it, right? And when I say assigning to clients, in order for those clients to access the internet, those addresses needed to be publicly routable, right? So for a server, let's say S, in order for this server to access the internet, it should have a public IP address or a IP address which is publicly routable. For example, 10.10.1.1. So whenever you want a machine or a client which requires access to the active internet, it would need a public IP address like this. And with the rapid boom of internet, what happened is that soon people started running out of such IP addresses. So it was really not feasible to assign every personal computer a publicly routable IP address like this, right? So people wanted to come up with a solution in order to deal with this ever increasing demand of IPv4 addresses and the shortage of IPv4 addresses. What the Internet Engineering Task Force did is it came up with a short-term fix, and this short-term fix was this concept of network address translation, or NAT. In short, what NAT does is it allows one such publicly routable address or one such publicly routable IPv4 address to represent a group of hosts on a local or private network. So what NAT in short does is, let's say this is our router and it's R, and let's say this is also our NAT box. This is also our NAT box. So let's say this router is connected to server S1, it's connected to S2, it's connected to two servers on a local network, right? And this local network is not reachable from the external world or external internet. And let's say these two servers are connected by this router to internet. So just for simplicity, I am assuming that this router directly connects these two servers S1 and S2 to internet, but in reality it might be different. This router might be connected to some more intermediate routers, and those routers might finally be connected to the edge router of your ISP, right? But for simplicity, let's just assume that this router R, which also acts as a NAT box, is connected to internet, and it connects this S1 and S2 to internet. So let's say this local network is something like 192.168.0.2, and this is 192.168.0.3. and this router, it has got two interfaces, of course, because one for this network, which is, let's call it 192.168.0.1, and let's say it has got another interface, and let's call it something like 140.140.2.1.5. So let's say this 140.2.1.5 is the public IP of this NAT box, right? Using this public IP, the router is connected to internet, and using these private IPs, these S2, S1 and S2 is connected to this NAT box. Now, in order to access the internet from S1, S1 first needs to send its packet to router, the NAT box. What S1 does is it tries to contact the internet using the port 8081. Application running on S1 is using 8081 port as the source port to connect to some server on the internet. So what this NAT box would do is it will maintain a table. So firstly, it will associate this in that table, which is called the NAT table. What it will do is it will associate this IP address 192.168.0.28081 to a new address where the source IP will be this NAT box's own external IP, which is 140.2.1.5. Okay, so it will associate it with this new external IP. It needs a port as well, so it will come up with a port. So if 8081 is available, it might use 8081 as well, or it will, let's say it comes up with a new port, and let's call it something like 5511. It comes up with a random port, and it associates this random port 5511 with this IP address 192.168.0.2.8081. So now this private IP address dot port combination is now associated with the NAT box's external IP and a new port number, which is 5511. Now what the NAT box will do is it will forward this connection, the connection attempt to internet, which it was making to some server on the internet, to that particular server. So let's say this is the remote server, and let's say its internet address is something like 130.1.1.2 for an example. Now the NAT forwards this connection, this request from S1 to the remote server. But what the remote server sees, the remote server sees that the connection is coming from 140.2.1.5:5511. So after generating the response, it will send the response back to this IP, not its private IP, because the remote server has no idea of what's the actual private IP address of S1, and neither it should know or neither it needs to know that, because this address 192.168.0.2 is never publicly routable. It will never be able to reach S1 using that address. So what the remote server will do is remote server will send back this packet to the destination address 140.2.1.5:5511, and when the response packet arrives at the NAT box, it will look up the same table and it will find out, okay, 140.2.1.5:5511 is associated with this private address, and it will send it back to the required application running on S1. So the work of NAT box is to maintain this table. So over the time, this table will continue to grow, and of course there is a TTL associated with the entries so that it doesn't overflow. So the primary task of the NAT box is to provide us with a translation between your private IP addresses and external IP addresses, right? So that a remote server on the internet can communicate with a private server in the local network, right, or the private network. So this in short is how NAT works and what NAT does. So before going to stun and what's the need of stun, let's first understand what are the problems with this setup. One very interesting thing to know about NAT is, as I mentioned, this was created as a short-term fix for the IPv4 address shortage, right? And just like several other short-term or temporary fix, this thing became permanent. So NAT became a permanent protocol and it stayed back with us. So what was supposed to be a short-term fix became a permanent long-term fix. Okay, so now let's try to understand what are the problems with NAT, and that would eventually bring us to the stun protocol. So the primary thing which we observed here is, like, just to mention this once again. So we have a server. The server sends its request to a router which also has NAT configured, and it sends it to a server on internet. Let's call it internet. This has a private IP address. This has got both a private and a public IP address. And let's say this has got a public IP address. Okay. Now, so far so good. Like, if this server wants to initiate a connection to the internet, it can always go via NAT. The NAT entry will be created and the internet server will be able to send back a response to our local server, and it works fine. But however, what about the applications which needs to locate a client or a client application which is present behind the NAT, and it needs to send some packet to that, right? So let's say we have an application on the internet which needs to send a packet of data or a IP packet to the server S. However, it doesn't know what's the private IP address of S is. So what about the application on the internet that wants to send a packet of data directly to this server S? Well, it can do that, but in order to do that, it needs to know the mapped external IP address and port for this address 192.168.1.2. Let's say application is running on port 55555. It first needs to know what is the NAT table entry for this particular IP address. It needs to know the external IP and port mapped to this private address for this particular application. And secondly, that mapping should first exist in the NAT box for NAT to forward the packet to the server when it comes on the external IP and port, right? So these two things needs to happen first before this external server can directly communicate with the internal server. So in this current setup with just NAT, that is not possible. Why? Because there is no way the external internet server knows the external IP for this internal application. It won't know which external IP or port on the NAT box is mapped to this internal application. And so in order to rescue us from this situation, another protocol was created which is called stun. Stun is not the only protocol which was created, like it also has got its limitation. So later several improved versions of stun came out, but in this video we'll only be discussing about stun. Stun also stands for Session Traversal Utilities for NAT. Let's see how stun allows this to do. So before moving on, this is a general use case and it's a very legit use case, and it's widely used right now in your real-time applications like your voice over IP, which internally uses a protocol called SIP, Session Initiation Protocol. And in voice over IP, the VoIP server needs to actually communicate with the node or the client, maybe on your mobile or on your desktop, which is maybe existing behind a NAT, right? So in most of the home applications, your PC is connected to your router, which acts as a NAT, and then again it's connected to maybe another router, and finally it's connected to the internet server. The external application has to traverse all this NAT to finally reach your home PC in order for your application to work. So it's a very legit use case. So one way the external application on internet can communicate with our server is if beforehand the server is somehow able to create a NAT entry for itself for this application which is running on 55555 in the NAT box. Somehow it's able to know what's the external IP and port that gets mapped to this private IP, and it is somehow able to register or send that external IP and port to the internet application which wants to communicate with it. If it's able to do that beforehand with the external server or the external application server, the external application server will be able to communicate with the internal server or the local PC, because now it knows which external IP and port in the NAT box or in the router represents our internal application. So stun is something which allows the internal server or any client to do that. So how stun server ideally works is something like this. So now we have got three components. So this is the stun server, and let's say the IP of the stun server is something called like 120.4 5.4.3, and the stun server usually runs on 3.4.7.8 port, and so this is the stun server. Before that, we of course we have the router or our NAT, and let's assume the NAT is, we already know its public IP address 140.5.5.2. again we have our internal server S, and it has this application running on port 55555, and its IP is 192.168.1.2. so now what the server S will do in order to discover its external IP address and port is it will first send a stun request, it's also called a binding request, to the stun server via this NAT. So it will contact NAT in order to reach the stun server. NAT will now create an entry in its NAT table, and let's say the entry it creates is 192.168.1.2.55555. let's say it maps it to something like 140.5.5.2 to some port like 44444, and it forwards this request, this binding request, to this stun server, and it changes the source IP in the packet that originated from this server S, and it replaces 192.168.1.2 with 140.5.5.2 colon 44444, and it sends it to the stun server. Now what the stun application sees is that the packet that it receives from the NATbox R, it sees that the source IP address is not 192.168.1.2.55555, but it's 140.5.5.2.2 colon 44444. Now what the stun server will do is it will generate a response where it will say that, so this is the response, it will say that external IP is 140.5.5.2 and external port, as I said, that this external port can very well be this port as well. There is no issue with that. And it says that external port is 44444. And what it will do is it will send back this response to this external IP external port combination, right, to the NATbox. And NAT will see that this IP is mapped to this internal IP, and it will forward the response to the server. So now what the interesting thing that happened is server knows its own external IP and external port. So now it has these two informations. And one more thing that the stun server can discover on behalf of the server, the internal server, is what type of NAT it's behind. So now it knows its external IP and external port. So now this internal server can register or send this external IP external port combination to the internet service which wants to connect to this server, right? So this is how stun helps in discovering the external IP and external port for a application running on an internal server in a internal network. So one more very important thing that the stun server allows this internal server S to discover is the type of NAT this client, the client application, is behind. And this brings us to the next thing, which is the different types of NAT that is present at our disposal. Okay, so before moving into the types of NAT, I believe this is a good time to mention that the stun protocol uses UDP as its transport layer protocol. The reason for that is UDP is a connectionless and stateless protocol, and it has got a way lesser overhead than TCP, and it has also got lesser latency. And also stun protocol is just one shot message receive and message sending protocol, so it really does not require all the features provided by TCP. So UDP perfectly suffices its needs. Now let's see the types of NAT that's present. The first type is full cone NAT. And this is the most easiest NAT to work with because it has got a way lesser restrictions compared to the other NATs. So first we have the NAT box, and we have a server, let's say S. Let's denote the IP of the server S as the internal IP as IS and the port as PS. And we have an external server or remote server R, and let's say its IP is R and port is PR. So when the request to this remote server reaches the NAT box, what NAT will do in case of a full cone NAT is, for a given for a given internal IP and internal port, it will always map that internal IP and internal port to the same external IP and external port. So let's say IS and PS is mapped to IE and PE. And no matter how many times this server sends a request to R, it will always map its internal IP address to the same tuple or the same combination IE and PE. So if S sends a request to R, or let's say S sends a request to R2, let's say this is called IR2, PR2. So if S wants to communicate to R2, even in that case, the same IEP external IP and port will be assigned to IS and PS. This also means if somehow these remote hosts, once if they know this IE and PE, that is the external IP and external port of the server, it can always send messages to this port, this IP and port, and the NAT box will forward that to our server. So no matter which remote IP or port the request is coming from, if that particular host knows about this external IP and external port for this internal server, it will always be able to communicate with this server. So in this case, this mapping is not dependent on the remote server from which the response is coming back or from which the message is coming. So that's full cone NAT, and it's the most simplest NAT to work with. So then comes restricted cone NAT. Okay, so a restricted cone NAT is a bit different from a full cone NAT in sense that in this case as well, like we have a NAT and we have an internal server S, and it's, let's say its IP and port is ISPS. There is a remote host R with IP IR, port PR, and let's say when S tries to contact R, the NAT assigns external IP and port like IE, PE. And so now the request goes to R generates a response. Now the response is sent back to NAT. When the response is sent back to NAT, in the response, the source IP will be nothing but IR, right? Because the response is originating from this server R. So when the NAT box receives this response where the source IP is IR, it will first check that whether previously a request was sent to IR. Only when it finds that previously a request was sent to IR, only then it will use this mapping and it will send back the response back to S. If the NAT finds that previously no request was made to the IP IR, then this mapping won't be used and the response will be dropped. So that is restricted cone NAT, and it's not as open as this full cone NAT. And then comes restricted port restricted cone NAT. And this is very similar to your restricted cone NAT. The only difference is that along with the IR, it also checks the PR, the remote port. So once again, we have a server S, internal IP IS, internal port PS. We have NAT box. We have a remote server R, whose IP is IR, port is PR. What the NAT now does is that when it gets a request from the server S, before forwarding it to R, as usual, it will map ISPS to IE, PE. Now the request goes to the R. The remote server R will once again generate a response, and in the responses packet, the source IP and port will be IR, PR. So this time we are considering the port as well. So when the response arrives at NAT, the NAT will check if there was a previous request that was sent out to IR and PR. Only if it finds that there was a previous request which was sent to the address IPR:port R, only then it will allow this mapping to be used and the response will be sent back to the internal server S. So if it finds that previously there was no request sent to the remote host R at IPR and port R, the response will be dropped. So it's a bit more restriction on top of restricted cone NAT in the sense that it not only checks the IP, but it also checks the port. Before moving further, let's try to understand why this restricted cone NAT and port restricted cone NAT makes life difficult for us. So let's say internal server, in either of this case, let's say this internal server uses a stun server to discover its external IP and external port. Once it has discovered it, it sends it to some external service provider, like for example a VoIP server. And when that new external application server tries to communicate with internal server S using its external IPs IE and PE, the response will be dropped at NAT. The reason being, this mapping IESPS to IEP was created for the stun server's external IP. Now, since the external application server will have a IP which is different than that, which obviously is different than that of the stun server, and the NAT won't find any previously sent request to that particular service provider, the response from that external service provider will be dropped at the NAT. So this is the reason the restricted cone NAT and port restricted cone NAT makes life difficult for us, and a stun server cannot fully help us in this case. So let's see the last type of NAT now, which also faces pretty much the similar issue. Symmetric NAT. What this does is, so let's say we have the same internal host with ISPS. We have, let's say, two remote servers, R1 and R2, with IR1 PR1 and IR2 PR2. And now when a request is sent from S to the remote servers, when it first comes to NAT, what NAT does is, let's say S is trying to communicate with R1. So S is trying to communicate with R1 via this NAT. So what the NAT will do is, it will assign IS PS to IE1 PE1. So you might have already guessed what happens here is, for any given remote host, it will assign a new external IP and external port to the internal IP and internal port. Depending on the NAT box, the internal IP might or might not change depending on the availability of the public address pool, but we'll just consider that both are changing in this case. It might happen that only the port changes, but what happens in short is that for every new host the internal server S is trying to communicate to, a new external IP port combination is assigned to it. So it is E1. Okay, so now let's say S tries to communicate to R2 via NAT. In this case, what happens is that ISPS will now be assigned to or mapped to IE2 and PE2. So if it again tries to communicate to another remote host R3, then a new tuple will be used. So even in this case, when an internal server discovers its external IP and port and tries to communicate it with a new remote server like a VoIP service provider or any service provider, that new service provider won't be able to send back its response or a request or any message to internal server S, because its response will be dropped, because that external IP and port combination won't be valid for the new service provider. So that is a problem with symmetric NAT. So restricted cone NAT and port restricted cone NAT are the two types of NAT which are present in the original NAT RFC 3489. However, the several vendors just differentiate NAT as full cone NAT and asymmetric NAT. Like they group everything under symmetric NAT, which is also called dynamic NAT, and full cone NAT, which is simply called static NAT as well. So these kind of, like, apart from full cone NAT, if your NAT configuration is one of the other three, just a simple stun server won't help you that much. You need an advanced form of NAT traversal, something like, as I said, stun is just a family of such protocols. The other more advanced protocols which are available at our disposal in these cases are a turn server or the turn protocol or the ICE protocol. And there are other methodologies as well, such as UDP hole punching. However, we won't be discussing about those protocols in this video. Okay, so now let's try to create a stun client from scratch in C, which will try to communicate with a stun server, and it will let us know what is our external IP and external port as seen by the internet, like our local machine's external IP and external port as seen by the internet, and also what is the type of NAT we are behind. Also, before jumping into doing that, one more thing I would like to point out at this time is, most of the real-time applications out there, or most of the voice-based application like VoIP, voice over IP, or the SIP protocol, these all of these protocols are based on top of UDP as their transport layer protocol. Most of these protocols use UDP in some form or the other. UDP is often referred to as a from scratch kind of protocol, which is used to create other protocols on top of it. So the reason why mostly UDP like protocols are used by these real-time applications is because of its low latency, and they usually don't go for TCP because all the heavyweight features provided by TCP like connection orientedness, statefulness, those things are not required here. Our real-time applications mostly depend on the application layer to assemble the data and do error prediction and those kind of stuffs. Okay, so now let's see how we can create a stun client. So the stun protocol uses binary encoded data to denote what kind of request is being sent, what kind of response is being sent, what is the various attribute types present in the request and the response bodies, and what are the attribute values. So now let's see how we can do those. First, as always, I will start with including some of the libraries or the header files. So we will be using UDP sockets. So now I'll be defining certain constants. First is the stun server. I'm using one of the publicly available stun server. This is the IP. You can easily find them via Google search. So 3478 is the 3478 is the standard stun server port. So this is the minimum request length. So I will be using 200 as the response length. And this is for a string to hold the IP addresses that we'll get from the response. Why 16? Because each octet of a IP address can at max be 3 digits, right? 3 digits. So 3 into 4 is 12. There will be 3 dots in between. So that plus 3 is 15 and 1 for the null terminator. So it's total 16. A tiny error function. So now we will define a function which will actually make the stun request. This is also known as a binding request, and the response that we get back from the stun server containing our external IP and port, it is called binding response. So first we'll take a socket FD. So the main function, we'll use the main function to create the actual socket and pass it to this function. Now we will take a stun host. Actually, we can simply use uint8t for this. Star stun host uint 16 underscore t stun port, because a port can maximum be 16 bits. This stun data will contain any custom data that we want to send to the stun server, and we'll soon see why this is required. So again, these pointers will be provided by, or these buffers will be provided by the main function, where we will store the external IP and external port. And with that, we'll also have something else, another IP address, which is changed host, and another port which is called changed port. Okay, so this might seem a bit weird that we are getting a pair of IP address and a pair of ports. One is external IP address and port, another is changed host and changed port. So why do we care about a changed host and changed port? Remember, I mentioned that the stun server also helps us to discover the type of NAT we are behind. So the changed host and changed port is used in order to do that. So what happens is when a normal binding request is made, along with the external host and external port, the stun server also tells us the other public IP apart from the one that we presented here that's attached to that server, and the other port which can be used to send the data from. Why this is required? This is required when we want to instruct the stun server to send us a response, the binding response from a different external IP and port apart from the one which we are using here. Why we do it? We do it in order to discover if we are behind a full cone NAT or a restricted cone NAT or a port restricted cone NAT. We will just see in a moment how it works, how we can use that. Okay, so these are all the parameters that this function will take: a socket FD, a stun host. Again, we could have simply hard coded this stun server macro, but we won't be doing that because of the same reason. Sometimes we would want to communicate the stun server on its alternate public IP. So now we have stun host, stun port, stun data, data length, external host, external port, and changed host and changed port. So now we will do the usual stuff to bind the socket to a local IP port and start sending some data to the stun server. So let's quickly get those default things done. So TRAN ID pretty much stands for transaction ID, and it uniquely identifies a stun request, and the stun response is also supposed to have the same transaction ID, and we can cross check that we are receiving the correct response which is desired for our request. So it can be just a random sequence of bytes, and let's quickly write a function that will generate us a transaction ID. This will be nothing but consecutively 4 bytes of random data. So in total it will be 16 bits. Cool. Let's call our function here, and that's tran ID, the buffer that we just generated, and let's just set our stun request buffer to all zeros. Also, let's initialize our stun server address with all 0. And now let's populate our stun request address. So for that we will simply just put in the required values for this address type. Family will be AFI NAT. This will be our stun port, and let's populate our stun host address as well. Okay, so before moving forward, what does htons do? So by default, how data is stored in memory depends on the architecture of the CPU that we are using. It either can be little endian or big endian. What htons does is it simply converts the host address or a host data from the architecture type of the local machine to network byte order, and network byte order is nothing but big endian, so that the network protocol can operate in the same manner independent of the architecture of the different machines the application clients or servers are running on, right? So htons simply converts everything into big endian notation. Let's continue. Let's give a info printf sending binding request to stun server. What we are going to do now is now we are going to populate the stun request with the various attributes, attribute values, and the request type, the request data length, and those kind of things. So let's do that. The request type is a 2-byte data, or rather a short. So an easy way to do is that we will typecast our stun request variable into a short type, or rather than short we can also call it uint16 type, and we'll pass the address of stun request and we'll do htons 0x0001. So 0001 denotes that this request is meant to be a binding request. Of course, we need to use the value at notation. The start will be here, not inside. So what we are pretty much doing here is we are saying that typecast the address of stun request. In this case, for the first element, stun request 0 and just stun request would have been the same thing. So what I'm saying is that just typecast this address of stun request to uint16 underscore t, to a 16-bit unsigned integer, and at that location put this data 0x0001, a 16-bit data, in network byte order notation. Then comes the request data length, which by default, if we are not doing a change request, it will be nothing but 0. Right now we will simply insert the next 16-bit as the transaction ID. So we will start with 4. We are starting with 4 because 2 bytes is gone here, and this is also uint16, so this is also 2 bytes. So we are starting from the 4th byte, and we will go for 4 more bytes. And we can simply do a uint32 star. Tran ID, and this is just a short trick to get the correct bytes from the tran ID, because we are incrementing I by 4, but we need to increment by 1 the index of trend ID. So it's just a quick calculation for that. There is no need to dig much into that, but yeah, nothing that important. So now basically what happened is okay, so one thing I would like to correct here, like I said, it's 4 bytes, like the next 4 bytes will be the transaction ID starting from the 4th byte, but that's not the case. It's not 4 bytes, but it's 4 into 32 bits. Rather, the next 128 bits will be the transaction ID. So if you see, like I am iterating 4 times, and this transaction ID is uint32 type, which is it can hold 4 elements, each 32 bit long. So that makes 32 into 4 128 bit, or rather 16 bytes, right? So that's 16 bytes and not 16 bits. So 16 bytes. So 16 bytes for the transaction ID, and we are doing the same thing over here. So I am starting with the 4th byte, and I'm iterating for 128 bits, or rather 16 bytes over here, because I am iterating 4 times, but each iteration is for 32 bits, so or rather for 4 bytes. So 4 into 4, again I am putting those 16 bytes of transaction ID into the stun request. Okay, so far so good. And this makes the base request, the base length of our stun request to be 20 bytes, 16 bytes for transaction ID, 2 bytes for the stun request type, and 2 bytes for the stun request data length. So now moving forward, we do a little check over here, and we say if stun data length equal to 0x0008 and stun data is not equal to null. So if it's a change request, the length of the custom data in the stun request is 8 bytes long, and in that case what we will do is we will simply insert that data after the transaction ID. Let's do that. 8 bytes is basically 64 bits, so we can directly use a 64-bit data type, and we will do stun request, and we will start from the 20th byte for 8 more bytes, and we will use the same trick which is very common in C. Okay, so all those stun data was a buffer of uint8 underscore t 8-bit type. So I am just taking the address of the stun data, I am just typecasting it to 64-bit, and I am directly inserting it at the 20th byte in stun request. So now we need to send this stun request to the stun server, and for that what we'll do is we will use the sendto call, library call, and it's just the function parameters for sendto. Let's just go to the next line for just ease of use, and we will do struct sock addr. Yep, so that's the full function call for sendto. We first send this, the first parameter is of course the sock fd, then stun request, and the length of the stun request, no options, so 0, then comes stun server address and stun server address length. So I would like to use the socket in non-blocking mode, so I'll just sleep for 1 second for the request to catch up, I mean, so that the stun server has enough time to process the request, and then I'll make a check if r equal to -1, which means we could not send for some reason. We will simply send back a -1, and then we will memset stun response as \0, and for the entire length of the stun response. So now we will attempt to get back the response from the socket or from the stun server. Pufflen 0, null comma zip. So we don't care about the source address or basically the address of the stun server. So I'm just passing null and 0 for the address, the remote address buffer. And now I'll do another error check. So if it's -1, we will once again return -1. And now we will start with the parsing of the stun response. Let's do that. First, let's make sure that we indeed have got a binding response and the transaction IDs match as discussed earlier. So let's just log what kind of message type we received, and I'll just print it in hex form. If r type not equal to 0x0101, so again 0x0101 or 101, it's the code that denotes that it's a binding response. So if it's not that, we will return -1. And I'll do the same thing to get the 16-byte transaction ID. I'll check 32-bit by 32-bit whether it's the same transaction ID that we sent, and I'll just do the reverse. So while sending I did a htons, and now I'll do a n2hl, so it will simply convert the network byte order to the byte order that's required by my CPU architecture. And once again I will do the same calculation, I by 4 -1, right? And let me just check I'm closing all the brackets. Yes, this looks right. And if any of them shows a mismatch, what I'll simply do is I'll return a -1. So now we know that our response is fine. And now what we'll do is we will pretty much scan the response and we will try to extract the external IP host and changed IP host of the stun server. So let's do that. So first let's extract the length of the message that we received. Okay, so again that will be a uint 16. It's the same as the request message. The length again starts from the second byte, and we will simply print it. Received message length. So once again we need to ignore the 16 bytes starting the fourth byte because those 16 bytes are the transaction ID. So let's start from the 20th byte, and we need two variables, one for storing the attribute type and another for storing the length. So now we will traverse the stun response. So while I less than size of stun response, so that will be a stopping factor. So first let's extract the attr type for this chunk, and once again we'll do a uint 16 because it's a 16-bit data, and we'll do and stun response I, and the other thing we will get is the length of this attribute. So now the remaining portion of this turn response is mostly in the form of attribute type, attribute length, and the attribute data. So we'll proceed accordingly. I plus 2 because this is 16-bit. And now before going into our attribute type check, what we'll simply do is we will increment I, right? And by how much we will increment I? We will increment I by 4 because of these two pieces of data, like the attribute type itself is 2 bytes and the attribute length is of 2 bytes plus the attribute length, because that's the length of the actual attribute value or attribute data. So now what we can do is we can check for what kind of attribute we have received. So if attribute type 001 and x host not equal to null, the attribute type 0x0001 is for external IP and port. So let's extract that. Once again, we need to do the network to host order conversion for short or 16-bit, and we will do so we have got the port, and what we'll do is we'll simply store this port in the required variable. So this will be capital P. Okay, X, it will be ext port. So now we have got the port. Next we need to get the external IP address. So that is also pretty easy. So IP address is nothing but 4 consecutive chunks of bytes. So total 4 bytes will be there. So uint 8. So I'll just denote it by IP1, IP2, IP3, IP4, or rather let's denote it as octets. Octet 1, stun response I plus 8, and I'll simply copy it, and I'll simply copy it and I'll paste it 4 times, and 2, 3, this is 4. Okay, so now let's use our favorite sprintf to print a formatted IP address in xhost. As mentioned, the maximum length can be max IP length str, which I believe is 16. And now let's quickly format our string. Octet 1, octet 2, octet 3, octet 4, right? So that is how we extract the external IP address and port. And now I'll just simply copy this and I will paste it again here, and this time I'll check for 5. So 0x0005 is the code that denotes attribute type of changed address. This will give us the changed address and changed port of the stun server, like the alternate IP and port that the stun server has. So let's extract that as well. So whenever we don't want to extract the changed IP and changed port of the stun server, we simply pass change host as null, and same for external host. Most of the remaining things stays the same. Instead of ext port, we'll do changed port, and this remains same, octet 1 2 3 4, and this becomes changed host and octet 1 2 3 4, and that's it. Now we have got our changed IP, changed port, as well as external IP and external port in the respective buffers that we will pass to this function. Now let's create our main function, which will create the socket, and it will use this function to get the external IP port and also determine the NAT type. So let's start with our main function. I'll seed the random function here so that we get some nice randomized numbers for our transaction ID. And now let's create our socket client address. We don't actually need to create a address and bind our socket to that, but I want to keep the port consistent across every runs of this program. So that's why I'll be associating a port with the client address, the stun client address, and I will be binding the socket to that particular address. So now I'll create the buffers for the addresses. Next, we will create another buffer for changed host. And again, it will be 16 into size of uint 8. And same for the changed port. And I will create some extra buffers for our temp host and temp port. It will just be used for storing the intermediate or the temporary addresses while doing our NAT type determination. So now let's create our socket. First, we provide the socket family, then the type of the socket. So as mentioned, we'll be using UDP, so socket datagram, sock datagram, and then I want to make it non-blocking. So that's why non-block, and the protocol will be UDP. Now if that is -1, if the return value is -1, then we can simply exit our program saying socket creation failed. Okay, and once again we will initialize the client ADDR. And then we just populate the client ADDR just like we did for the server ADDR. And here I'll be using a particular port, that is 54320. You can choose any port of your liking. And here we'll be providing the source IP address as well, and this will just provide with the macro inaddr. So it will pretty much bind to all the interfaces. Okay, and now we are going to bind our socket to this address. And once again we check if it returns -1 or -1. If it does, then we simply once again exit with error and we do a bind failed. We need one more buffer to store our change request, and that we will call as stun data, and it will be 8 bytes as we saw earlier. And we will also store this. We can actually use scat because it will be a string type. Actually we'll be storing a string here, and we'll be basically storing the NAT type in this variable. Okay, so now let's create our change request, and so that we can use it when required. So for that, what I'll be doing is, once again I'll be providing it with uint 16, so 16-bit types. And yeah, I'll just be explaining what the different bytes mean in change request context. So the first 4 bytes are pretty much hard coded. It will be 0x0003, and then it will be that's a typo. And then on the second byte, onwards from second byte, we will put in another hard-coded value, and that's 0004. So this data pretty much denotes that the binding request is a change request as well. So it's instructing the stun server to send the response from a different address. And next we will tell it what kind of change do we want. Do we just want to change the port, or do we want to change both the port and the IP of the response source address? So in this case I'm going to change both the stun server response IP and port. So let's do that. So 2 bytes already gone. This will be putting at the 4th byte, and once again this is another hard-coded value, and this will be 6. So it's basically 4 bytes. That's why 32-bit. Now we will make the stun request using our function that we created earlier. So first, the stun server IP that I'll be using is the one denoted by our macro, which is stun server, and the port will also be the one denoted by our macro. So let's see what is the 4th parameter. 4th parameter is stun data. Of course, this is not a change request, this is a normal binding request, and hence I'm not changing any change request data. Length is 0. Host, port, changed host, and changed port. So that should be sufficient. And let's quickly print external IP and port that we received. We can also actually print the changed host and the changed port just for the record. So let's do both. External IP So now what we are going to do is we are going to simply print this external host, and then I'm going to print the external port as seen by the stun server. So this external IP and port is basically the external IP and port that NAT server is assigning to the internal IP and port of our local machine. So for any external service running on the internet, our local machine will be appearing as this IP and port. Okay, so now we have ext port. Next, let's just put a heading as well. Data returned. I'll just put a extra line from the debug logs in our stun request so that we don't get confused. We'll call it data return from the stun server. And actually I was going to put a extra line which I forgot. Okay, now I'll simply copy these two lines, and what I'll do is I'll call it changed IP, and changed port, changed host, changed port. Okay, and we'll do a tiny error handling here as well. If r equal to -1, exit with error, could not contact stun server. Now what we are going to do is we are going to make another stun request, and this time we are going to instruct our stun server to send us the response from a different external IP and port, or rather a different public IP and port. So once again we will use the stun server and stun server port. Now we are sending a stun data. The length is of course 0008 or like simply 8. We don't want to override our initial external IP and external port that we found out, so we'll just use temp host and temp port, and I don't want to store the changed host and changed port this time, so I'll simply send null and null. So what we essentially did is we asked stun server for our external IP and external port. Now what we are doing is we are once again asking the stun server for our external IP and external port, but this time we are instructing the stun server to send us the response from a different public IP and port on the stun server. So if this works out, if we are still able to get back the response, it means our NAT type is full cone, right? Because a static mapping has been created between the internal IP and port of our local machine and the external IP and port of the NAT server or the NAT box. So that means if this works out, it means we have a full cone type NAT. So let's see, if r not equal to -1, we can say that the response was able to reach us and we have a full cone type NAT. Else, in the else part, if we go into the else part, we are sure that our NAT is not configured to be a full cone, and then we need to figure out what kind of restriction is our NAT imposing, right? So let's see that. Now what we'll be doing is we'll be making another stun request, right? And this time, instead of using stun server and stun server port, we'll be contacting the alternate IP and port of the stun server. So in a moment we'll know why we are doing this. Changed port. We want this to be a normal binding request. We'll send null comma 0 for stun data and stun data length. And once again, I don't want to override my external IP and port of my local machine, so I'll be sending temp host and temp port. And I don't want to get the change request and port, so I'm just going to send null null. And now let's do a preliminary error handling. If r is -1, then we can simply say printf. Actually not printf, we can exit itself. So exit with error, could not connect to stun server on changed host and port, right? So yeah, that's that. Okay, else, now what we are going to do is we are going to compare the original external IP that we received from our stun server with the external IP that we received right now on contacting the stun server on changed host and changed port. So that's denoted by temp host. And we are also going to compare the original external port that our stun server responded to us with the current external port that we received as a part of this current request. So let's do that. So I'm going to use strcpy for that. So strcpy x host comma temp host. Import. So if this is same, then we'll make a couple of more checks. But if this is not equal, so if this condition fails, what it essentially means is that when we contacted the stun server on a different IP and port, the external IP and port that was mapped to our request or that was mapped to our server by the NAT box changed. So what does that mean? It means that when we are contacting a different host IP or a different remote IP and remote port, the NAT box is associating a different external address to our internal address of the server. So what it essentially means is that the type of our NAT is a symmetric NAT. So remember, symmetric NAT is the one in which whenever you are making a request to a new remote host from your local server, the NAT will be mapping your internal IP and port of your local machine to a new external address. So we can now surely say that we are behind a symmetric NAT, which is not a very good news for this kind of real-time peer-to-peer applications. Okay, so let's say if they are same. If they are same, we are at least sure we are not behind a symmetric NAT. Now we need to check whether it's a a restricted cone NAT or a port restricted cone NAT. For that, now what we are going to do is we are going to send another change request to our NAT server. That is a binding request where we are instructing the stun server to send us the response from a different address, but this time we will keep the IP same, but we will just change the port, right? We will instruct the stun server to keep the IP of the response message same as the one that we contacted it on, but just change the port. So for that, what we'll do is we'll simply tweak our request data a bit. So the 4th byte onwards, we will change the code, and now we will send this. Okay, so instead of the code ending with 6, now it will end with 2. And once again, we will use our stun request function to send this change request. Stun data, and it should be 0x8. Once again, we are not interested in the changed host or port. Okay, and now, so remember we just changed the alternate IP is still the same. We are not using the alternate IP for the stun server response, but the alternate IP is same as the stun server host. So now if this R is not equal to -1, it means keeping just the IP same worked. And that means the NAT type is a restricted NAT. If it didn't work, if on changing the port, the response failed and it couldn't reach our server, that means our NAT type is a restricted port NAT. You can add the words cone here too. Yep, that's how we determine the NAT type of the NAT behind which our local machine is. So I'll just put this thing below. And I will also put NAT type. And NAT type. So that's how our stun client looks. So now let's try to compile and run it. So as always, let's first use GCC to compile it. and there is some problem. It's on line number 42. Let's see what's going wrong. Okay, this should be iNet 8 on. Let's call it iNet 8 on. 8 on, and let's try to compile it once again. And it compiled. Let's run it, and we got a response. So the NAT type that was discovered for us is full cone. So my machine is presently behind a full cone NAT, and so the external IP that was discovered is this. So I got back the external IP address that was associated with my local machine as well as the external port, and also I can see two logs here. So two messages to the Stun server was sent. One was a normal binding request and another was a binding request with change request data incorporated into it. That was like two requests that were sent to our Stun server. And since it's a full con NAT, the code flow got over just after the first test. Like this must have returned non-negative. So this was NAT type cone and the flow got over. So yep, that's how we can write a simple stun client in order to determine our external IP port and the NAT type of the NAT we are behind. So again, like if you search on the internet, you will find number of stun clients. Some of the clients are already embedded into the applications, the P2P or the real-time application libraries provided to you. You mostly won't have the need to ever implement your own stun client, but this is pretty good for understanding how a stun client works or how a stun server works, right? And how to determine what kind of NAT we are behind and all those kind of things. So yeah, these are the things I wanted to discuss in this video. What is NAT, how it works, what are the different types of NAT, what are the problems with NAT, and how a stun server can help us. So yep, that's all for this video, and see you all next time.